All right, so now let's look into geometric progression, which is the next sort of thing about that we're going to look into. One thing with geometric progression is it often reminds us of like the powers and things like that. So you might like recognize some of these ahead of time, like, like for example, this one, it's like very recognizable. But in essence, what a geometric progression is that you take a term and you multiply the next term by the same number each time. So what it is that if you have a, the next term is ar, next term is ar squared, ar cubed, so on and so forth, where the nth term is ar n minus 1. Okay, and oftentimes when we have powers and things, like I was stating before, it's like a geometric progression, but with like a ratio. It starts out, with 1, and then it has a common ratio, and so that's like powers. Like I said again, the nth term is written this way. About the sum of n terms, the first n terms of geometric progression, you can write this as a sub 1 times r to the n minus 1 over r minus 1. So this is something that I would definitely memorize, at least know how to get there. And if we have, for some reason, an infinite geometric progression, it's very rare that it'll have a common ratio greater, like that has an absolute value greater than 1, because that would be divergent, and meaning that it wouldn't have a value to come to, like it doesn't approach a value. And so in this case, we are looking at so we're looking at the fact that, okay, n is equal to infinity, and that's equal to 0. So r to the power infinity would be equal to 0 because it's, 1 over a, or 1 over, let's call this 1 over k to the power infinity. Sorry. And you know that, like, if you keep on multiplying like a fraction less than 1 by itself, it just keeps getting less and less and less. So this just eventually gets to 0. And so all this is 0 minus 1 divided by r minus 1 times a1. And so that would be a1 over 1 minus r. And so that's where we get our nice sequence from. So an example of this is if you have like 1 plus 1/2 plus 1/4 plus 1/8, so on and so forth, like infinity until like infinite terms, then this can be written as 1 over 1 minus half, because the common ratio is half, and then that just be 2. The proof for the sequence wherein we have n terms is of this form. So you have that s is equal to a1 plus r times a1 plus r squared times a1, and so on and so forth. So what you do is you take a1 common, and then you have these terms. You multiply these sequences by r. So you get that s is equal to a1 plus 1 plus r1 plus r2, oh sorry, my bad, r squared plus so on and so forth plus rn minus 1, right? But then rs is equal to a1 plus r squared plus so on and so forth plus rn minus 1 plus rn. So now what you do is subtract, so it's s times 1 minus r, and that's equal to a1 times 1 minus r to the n, and s is equal to, as a result, a1 times 1 minus r to the n minus 1 minus r. And so that basically is how you go about it. And then obviously the way that it's been written is if you take the negative sign out on both sides, so on upper and lower, and so you could write it as this form as well. So that's basically how you get this. And often multiplying the sum by another number that and kind of staggering it and canceling out terms can be a very useful way of coming up with a closed form for the sum. So let's dive into an example. And before I go into an example, I just wanted to tell you guys something about the tricks in some sense of arithmetic and geometric progressions. And so what I wanted to tell you guys is that when you have an arithmetic progression, you have like a certain number of terms, oftentimes it can be useful to identify these terms as like a minus 2d. Let's say you have 5 terms, then a minus d, a plus d, and a plus 2d, because when you multiply things, so a minus 2d times a plus 2d, you get an a squared minus b squared form, and that can be pretty useful to simplify, like easy to simplify. So that's why it can be very useful. And on a similar note, like, so this can often be confusing, but for geometric series, you want to stick with your normal forms, like AR squared, so on and so forth, because you want to try to avoid fractions. So just make sure that your approach for either one is, sticking with that form. Okay, so with that, let's read the next question, and I'll give you guys some time to solve it, and then we'll come back and discuss. So the sum of an infinite geometric series is a positive number s, and the second term of the series is 1. What is the smallest possible value of s?